Good afternoon, April 12th, 2023, Seattle, Washington. It's quite pleasant outside. Today, we'll continue listening, hearing, thinking, reading, talking about the path integral. The path integral is that there's a superposition of the states that a path can take. The high road and the low road, as it were, or as about that it's a wave, and so the wave's real action kind of is so modeled that then it results that the discretization of the particle, it's bringing into being as a discrete thing, is an action of sorts. It's as an effect. It's something that occurs, that it's an event. The event is. Also, the fundamental thing when we talk about probability theory, it's a thing. Anything that happens in a probability happens in a space or a support space of all the possible events. What is any one given event as the notion of the sample? It's from the sample space, the support space, as it were, this event. And so in the probabilistic interpretation of quantum mechanics, or the Copenhagen interpretation, which is kind of at odds with the Bohm de Broglie real wave function collapse interpretation, has that the probabilistic and stochastic behavior of particles over time as waves in a train is so what results is that it becomes the measurable phenomena. It's what's observable. And so then when we talk about the observation and measurement and sampling effects, that these are what go into both the interpretation of the events as stochastic, as governed by random behavior, while that there's no memory between events, that they're independent and identically distributed in distributions without bias and distributions without memory and this kind of stuff. That the probability theory advises us on how to describe events that are stochastic. And another thing that the Copenhagen interpretation has about the path integral and why the path integral is built upon the formalism is that the real wave function collapse basically describes a supermodel. When we have our models based on our sensory inputs, they're based on observables that we can monitor in time. And these sampling and observation and after measurement effects make it so that it's possible to define it in terms of the stochastic when it's not so much available except to reason the idea that things happen instantaneously at 2 points and once and come together, or that when there's the interaction of the wave and the real wave function collapse occurs, that it just so happens that was the sum of the potential, the most likelihood of the existence of the event, which is as well modeled as potential, so that it can work out that there's just a random stochastic nature to things, but at the same time it's all cosmic clockworks, that the real wave function gets one to thinking about how things can be these supermodels. And so that when we think of something like the rate of flow or flux, that it's like flow is flushing and flux is fleeting. That that on either side of what's either as the boundary, that we usually think of it as diminishing towards zero, but in the other sense it's retreating towards infinity. Objects in the mirror are farther than they appear. Objects in the mirror rapidly disappear. There's these kinds of ideas that get into why, when you want to set up a further, fuller understanding of the path integral, then it involves not only just the statistics of the bosons and fermions as they're empirical and as they come out and about, and as these diagrams help to so connect them and help explain on the order of the fifth order difference from unity, that these path integrals work up in usual caustics and as of after refraction, and that they're optical, and that the discretization of the particle is as it arrives at a point and as it comes into that, like a tiny black hole or a singularity of velocity, that this spiral space-filling curve or the funnel, the vortex, the flush of it, as it were, makes it so that this kind of modeling is how it adds up that quantum mechanics is so profound, because it reflects our ability to make things that understand and are based on effects, that these devices in the apparatus are as a science above the limits of our view, and beyond the resolution of our focus, as well beneath the microscopic, what yet makes the emergent. For these questions of like, why is thermo first law different than thermo second law? It's not. These are the kinds of things that get into the superclassical in physics. And so then when we point to somebody like Fritz London, who is involved in the initial developments and the concepts of the superconductor, with which you might be familiar because the room temperature superconductor is basically the temperature of liquid nitrogen, which is 100 degrees below zero. That there are certain ceramics that enable it to show that given a permanent magnet in one of these ceramics, that by cooling it down to where it's superconductor, that it will float in an electrical field, a magnetic field, the combined electrical and magnetic field that represents the motion of current and is after the establishment of permanent magnetism in the ferromagnetic, paramagnetic, diamagnetic, in such regimes. And this is among the reasons why that the lettered fields of potential of the electromagnetic fields are not just E and B, Maxwell's classical fields, which of course have their perfect solutions that are close approximations to first order in terms of what's measurable, what's observable, and also what's easily calculable, eventually in formulas of circuits that the voltage difference, or potential difference, as it's called, voltage, the electromotive force is as well modeled as voltage difference as what affects the flow model of electricity, which we talked about is different than the flow model of liquids like water or oil. That these are the kinds of things that get into why there's built more of this description of the intuition of the superclassical, because it's how it's so arrived at these nonlinear contributions, the higher order, the conditions at singularities, and even for probability theory, what advises events, and as what is stochastic, and how to build stochastic besides as above counting arguments, and usually means of symmetry and reflection and regress, these kinds of things. And there's also that then higher level mathematics come into play about these different definitions of continuity, as we've been discussing, that are like line continuity. It's definition of a continuous mapping from continuous domains together and apart for these Jordan measures, line elements that otherwise are these unfortunate bastard degenerate phenomena in otherwise the theory of measure theories, because at once it is this thing, but it's non-standard, so it's not this thing. And similarly with the Dirichlet function, rationals and rationals, each dense, each disjoint, each together forming as a complement the reals, that mathematics sees why there's this definition of signal continuity, which makes it so for that then with our usual field continuity and also the usual notions of the discrete and continuous in these fields, and it has how all probability theory is already built this way, that it comes together as a cohesive whole instead of what's eventually utterly in extremis when you would otherwise blindly in a test replace one with each other. They would be inconsistent and contradictory. So this kind of replete formalism is what's up above the complete ordered field, which for its purposes and as is so, we have all our great extended formalism, that these superclassical notions become retroclassical again to fulfill the desiderata and requirements of a theory, of a mathematics, thus that then can equip physics, a mathematical science, with the needful, so that its models are not bereft of meaning nor validity. and insofar as then they may be well-founded and sound. So with that said, what we're going to do is look at underneath this Descartes' discourse on method, and in another talk we've been talking about the differential and the differential equations and nonlinear partial differential equations, and there's differential geometry and the differential topology and quantum field theory. Now this is related to the field directly of the path integral and quantum field theory. We have quantum electrodynamics about the electrical fields, and we have quantum chromodynamics about the kinetic fields, strong nuclear force and the electrical force, respectively. So QED was Feynman's forte, and his electron physics after Millikan basically pegged, as he measured, the value of an electron's discrete charge as a finite quantity for one electron in an atomic physics. And it says in the current and over time, and there, it kind of remains to be seen how it results that the Millikan oil experiment is as well theory and resonances, and as otherwise of the stochastic behavior of such things, which can help us understand that the quantities are vanishing. Vis-a-vis the wave train, it drives such a notion as array of things. So when this quantum field theory, has that there's both quantum electrodynamics and quantum chromodynamics. And one wonderful thing about the quantum chromodynamics is that you've probably heard of the quark. And so the quark is the idea that our atoms are what's called the atomos, the atomic. They cannot be cut. They're not cuttable. Atomic. That atomicity is something that can be cut. And so they're elementary particles. They're fundamental particles. They're atomic. So anyways, within the atomic structure, and there's various models of like the billiard ball model of neutrons and electrons, as that the atomic number basically has reflected that there's the atomic mass unit, and the atomic number is how many protons an element has. And it just so results that according to the protons, which the idea is that protons are what are held integrally internally to the nucleus of an atom, that then the electron is the wanderer, or insofar as how in the electrical current that does not change the fundamental elementary state of matter at rest, that these ions and ionizations and binding potentials are the story of how the surface, which is a flat surface and is really only discrete to the level of atoms in terms of it being affected, being picked up by these processes that happen to produce this refinement precision down to the fundamentally discrete in the atoms. That in the nuclear model, then there's the atoms of their protons and neutrons and electrons. And that fundamentally the model is as about the electrons are in orbitals, and they're variously stable or astable. Their presence in a given fixed number of orbitals. That a book like this geochemistry book that we looked at the other day, and all about the inorganic chemistry, really helps explain how our model is arrived at after Millikan and after J.J. Thomson and this kind of thing. That for electron physics and Feynman, that there's this proton physics of a sort, where these are Pauli's particles, and so the atoms all are distinct and don't share the same place, but they're otherwise equal and not different. So they form a lattice in an array, and so that's the Pauli's principle. And then there's also that the nucleus is formed of protons and neutrons, which contribute to the relative molality of quantities. That the electron mass, by the energy in it, is a constant, or it's measured, and there'll be a discussion later about the running constants. That over time, as the electron value and atomic atoms are measured more closely, they get smaller. Not just more precise, actually smaller and more precise. And this is called the running constants and why it gets into the regimes of the infinitely small and infinitesimal and infinitely large, the infinite, these things. And it also helps to explain then when we get to the discretization and that we've established what the constants are, that these constants then in the molality add up for the Avogadro's number, some 10 to the 23rd, or 10 with 23 zeros after it. Many of these, that then the atomic numbers of the atoms, which are the protons, and the atomic weights of the atoms, which are the protons and the neutrons, where a neutron is about the same as a proton, and it's theorized that it's kind of a neutron, an electron and proton together, or apart. It's theorized that way. That then there's in the quantum chromodynamics, there's even that the color force is that these protons and neutrons are still not atomic. That they're modeled as fields, as particles in the zoo, because they're artifacts in this flux and fleeting, or flow and flush, to these ratios as they go to infinity, and about how they maintain this form of proportion. That these are the quarks, the Quarkian physics, and it's about the trans-Planckian regime, and it's about angstroms, which are very, very, very small measures, and have to do with the high precision of the electromagnetic apparatus, which is able to discern quantities on the order of the atom, like the scanning tunneling microscope, which is still quite large to these things. And then when you think about atomic deposition and all that kind of stuff, it's as if a spray of these things. It's a continuous process. And then when the detector actually picks up these things, it says of a very, very, these very interesting properties, why, after the ultraviolet catastrophe, things are discrete and fixed and constant. And it varies over time, according to the configuration of the experiment and the energy of experiment. This is where something like for something like the Weber bar and something like the cloud chamber, and these days we have the superconducting super colliders and this kind of thing, that there's all kinds of these configurations of experiment that could be redone for a lot less money, for example, than a super collider, that would really help to illustrate that these running constants are real. And so then it helps to explain all these things that go on in the mysteries and the confusions of quantum mechanics, that they're not. They're resolved by figuring out that it's just matters of configurations and energies of experiment. Well, that's so, then making that tractable, besides it's sensible, it's still not yet so fungible. It's intuitable, and thus it arrives at it as sensible, but then to make that fungible and result at tractable, first of all, we have to deal with the bulk of our methods that have defined all these things, that if we want to build an apparatus with given dimensions, it's got to add up. And another thing is that then with regards to these derivations that are all built up, you kind of have to rederive the whole thing if you're going to start from these higher level terms, because otherwise you end up kind of trying to put a classical theory and a theory of potential together, and it's only in kind of particularly contrived things like the ring gyro, the laser ring gyro, where it happens to so add up. And things like nuclear magnetic resonance, where it's applied that resonance theory is what works up, how it works out. Effects in physics. All right, so this quantum field theory, gets into quantum topology, and so there's things to do with what it does line up and work out, and then what goes on. He talks about operators, and so the operator theory is like how we deal with our zoo or our plenitude of these algebras and their varieties, and then the operators and pseudo-differential operators. I'll be curious if that was, because the pseudo generally will reflect a degenerate. That it's as of what would be elementary. It's kind of with respect to it. It's an element almost, a prototype of a thing. Yet like a degenerate interval has no middle or something like that. That a point is a degenerate interval. Or that a point in a line is a degenerate thing of a point on a line, or this kind of thing. Here the idea of the pseudo-differential operators is this kind of thing. And so just as for reading a sampling of it and to help fill the context, to help establish the intuition, I'll be curious to look at what that is. And so then the rest of this book gets up into the instantons and monopoles. So the instantons and monopoles is basically making for the this singularity again. When something is discretized at a point, it's kind of like, not only does it have to, it's not like a focus and a particle's linear path or wavy path. Usually as people think that this particle just moves kind of in a wavy motion, but it's really just the wave front of a wavy wave. As so it arrives, then when it's discretized, it's made a particle, that it also kind of is collected in the detector. It's coalesced there. This is the effect, or the idea of the thing, that the classical standard physics of the day has built up in a classical linear and standard framework. What here is being described in a superclassical framework, and that there are means to help mathematics provide physics the equipage, so it has models of these things, and that thus becomes sensible, fungible, and tractable. So then this book, after the instanton and the monopole, which is that there are no magnetic monopoles, it's a theoretically non-existent thing, because it's only in the extremis of otherwise our transitions in electromagnetic fields. It's like the straight line of the classical function, the asymptote, simply doesn't exist. But at the same time, it's as an ideal thing, it's like when all else is pointing the other way, it's just kind of like the shadow of a projection. That light is more like a shadow of things than a light of things. Besides the intensity, there's the shadow. These are some of these kinds of things. And it's all a lot about the complementary, the reflective, and how things are neat. So here, I want to read about the pseudo-differential operators, because I want to see how that's going to advise us to keep reading path integrals and quantum processes, thus that we can arrive at what is more of chapter 3 and getting into what is, again, promised to be kind of more of the building the intuition that helps arrive at why the methods apply, and then what to figure when they break. Because any particular device and apparatus that's not this imaginary contrivance has factors. So I'd like to see, he discusses ellipticity. Nash discusses ellipticity about a bundle isomorphism. Note that the symbol of delta P, though a matrix, is a multiple of the identity, however. The symbol sigma 1 d star xk is a non-square matrix. And about generalizations of, here the Laplacian. The Laplacian, kind of like Hooke's law, is in a lot of different places. It arises in pretty much all these ways that we've converted the continuous to the discrete in the classical. So the Laplacian shows up a lot. Pseudo-differential operators. We are now ready to introduce our most general kind of elliptic operator. This is what is known as an elliptic pseudo-differential operator. First, we must define the term pseudo-differential operator. We accomplish this by abstracting to a more general situation the main properties of the symbols of standard differential operators. If P is a general operator defined via its symbol sigma x comma P by the equation P u of x equals the integral over Rn of sigma x comma P u hat P exponent negative IPX dp, then P is said to be a pseudo-differential operator of order M if its symbol sigma x comma P belongs to an appropriate space of symbols which we denote by s to the m omega. So this is the idea that kind of like this functional theory, and the theory of some potentials, where it's a theory of harmonics, but that's still only the finitely many. This is again discussion of an infinite space and how it arrives at what's a degenerate of the one, but elementary in the otherwise the other way. So they can add up both sides of what results these vanishing evanescent outer products that ends up making a trace and inner product. This is kind of the way of things. It remains to define the space Sm to omega, and to do this we simply try and imitate the standard situation where one thinks loosely of the symbol as being a polynomial of degree m in P with x-dependent coefficients. As a definition that turns out to work as the following. Definition: symbol space. Given an open set omega and subset Rn, there is a symbol space S to the m omega with m in R, which consists of those functions sigma xp, which for x comma p in k cross R and n, with k a compact subset of omega, satisfy the condition, the absolute value or determinant of d sub x alpha, d sub p beta, sigma x comma p is less than or equal to a constant alpha comma beta of k, or c alpha beta k, 1 plus quantity absolute p or determinant p, m minus absolute beta, where c alpha comma beta k is a constant. Before taking the next step in defining a pseudo-differential operator, we have some observations. First, we point out that the intended definition of a pseudo-differential operator P has as its main idea that P is pseudo-differential of order m if its symbol sigma x comma p belongs to Sm omega, big omega. Next, notes that we have defined Sm omega for all real m, thus the order m can be non-integral or negative, etc. In fact, we shall also encounter examples with infinite m. Thus, we will be able to deal with operators of any real order, finite and infinite. Observe too that if sigma x comma p belongs to S to the m omega, it also belongs to S to the m plus 1 omega. Thus, if an operator is of order m, it is also of all higher orders. This suggests that the order be defined as the lowest possible such m, the infimum, say. We do not do this because this infimum may not be attained, i.e. it is possible to encounter cases where an operator is of order m plus epsilon for all strictly positive epsilon, but we cannot pass the limit where epsilon equals 0. See also the example in 2.62 below. We can now give our general definition of a pseudo-differential operator. Pseudo-differential operator of order m. Let m be a compact n-dimensional manifold and u and v be vector bundles of rank S and R respectively over m. Denote the corresponding space of sections by big gamma m comma u and big gamma m comma v respectively. In P, thus that gamma m comma u is taken to gamma m comma v is a pseudo-differential operator of order m if for any choice of open set omega subset m with the local coordinates x comma p, all the entries of the R cross S matrix element sigma x comma p belong to S to the m omega. With this very general definition, we also have to say that what is meant by the leading symbol sigma n m x comma p when sigma x comma p is the element of S to the m omega. Having in mind the case of differential operators in order m where the leading symbol is homogeneous of order m as a function of p, we are led to make the following definition. Definition, mth order symbol. If p is a pseudo-differential operator of order m, then its mth order symbol, sigma m x comma p, is given by the limit sigma m x comma p equals the limit as mu goes to infinity of sigma x comma mu p quantity over mu to the m. We wish to point out that in this definition mu is positive, thus mu sigma m x comma p satisfies sigma m x comma mu p equals mu to the m sigma m x comma p for positive mu, but not necessarily for negative mu. For example, sigma sub m x comma p could be the function absolute value p to the m, and then p would be a pseudo-differential operator similar to the example considered in 2.61 below. However, if p is a differential operator, not a pseudo-differential operator, if p is a differential operator, then we will have sigma m x comma mu p equals mu to the m sigma m x comma p regardless of the sign of mu. If necessary, we shall refer to this homogeneity property possessed by the leading symbol of pseudo-differential operators as positive homogeneity. So in this case with a degenerate, then there's this positive homogeneity is what arrives at the degenerate case still has a regenerate, emergent regenerate function. That then this pseudo-differential operators are operators as about the pseudo-differential, and there are conditions where they implement also the differential. And so the idea is then that these models of these things can replace what's otherwise a differential model as a differential model in accordance with these elements that are after means methods of exhaustion or in the infinite and real, as he says, that it's a thing. And so that gets into equations. There are some functions that, for example, for all finite terms go to a limit that is infinite and positive, but at infinity there's 0. This is an example of a kind of a degenerate function, or they're not quite the same thing as a standard function. with the idea of there's a thing called what's called a super task. And so everybody knows the theory of the limit, and we get closer and closer and closer again, and that's how we can work tractably with infinite induction and make it so that we can say that all the inverse powers of 2 go to 1, their sum goes to 1. The limit is the variable carrying them, the partial sum goes to infinity, always gets closer to 1, there's nothing less than 1 you can found not passed, 1 is never passed. It's infimum and supremum. It's least upper bound. It's 1. Yeah, that here it's similarly so when he starts describing how these things would, thus require that in this projection coordinate we have a variable that's infinite, and it's an infinity, and there's a value for it. And for these pseudo-differentials, essentially different than these differentials. That adds up that otherwise the linear terms here in this context don't contribute more than they provide. So that it works out that then what results is compensative arrives. And so that is a pretty hefty definition, pseudo-differential case. And then he goes to define ellipticity, which has regards to our curvature and relativity, because these models are also effective about relativity in its models of continuity, just as much as it is for the quantum particles in its models about continuity. That the pseudo-differential is a key definition here of Nash's book. So I'm going to put this down because later he talks about anomalies from a Hamiltonian perspective. The Hamiltonian after the Lagrangian, after the Laplacian, some linearizations for tractability, where the derivation has to be branched from and built from to arrive at a rederivation of things, to get to the replete. What we had was complete, but incomplete. Or what we had was complete, yet eventually inconsistent with its own other constructions. It's replete, superclassical. It's how it is. All right, so, and then he talks about the Virasoro algebra, and so I'm just going to look at that because that's in these systems where we talk about like the virial and the perturbations and the variational principles. I just want to refresh my memory of what that was briefly. These touchstones of the names of the people is really a key thing because it's not just a few formulas or like their results, but also it's the context of who they are, where they're from, what their other expectations would be, who is clubbed together and how. All this kind of stuff reflects this, again, these eternal exhibits in David Hilbert's Infinite Living Museum of Mathematics, which equips physics. So he talks about conformal invariance, which is usually, bedrock, solid. It's Noether's theorem. Symmetry implies a conservation law. Here that is continuity laws actually are a more fundamental case, degenerate or more fundamental, that end up adding how the degenerate makes up these things. Energy momentum, conservation condition. And then I wanted to see what this was. Relation to the Virasoro algebra. We know from chapter 6 that the conformal group in 2 dimensions consists of the group of holomorphic and anti-holomorphic transformations. The conformal group. More precisely, we can realize the 2-dimensional conformal group as a product diffeomorphism S1 cross diffeomorphism S1. 1S1 corresponds to the boundary values of the holomorphic transformations, the other to the boundary values of the anti-holomorphic transformations. Using the holomorphic and anti-holomorphic energy momentum tensors TZ and T bar Z bar, we can construct the generators of the corresponding algebra. So he's setting up the symmetry conditions and these reflexivities. It's complementarity conditions about our unitarity, which is an SUN or SU big omega SU infinity gauge theory. And thus the L sub n generate a Virasoro algebra from combining the operator product expansion that the generators have the commutation relations that their commutators flatten out or zero. That they have commutation relations, where the non-commutative algebra is sometimes just like attenuating or growing commutators. They're still commutative, they just have terms. instead of being non-commutative or anti-commutative, they're supercommutative. It's this kind of thing, where extra and super basically mean the same thing, and sub and super are antonyms, and this degenerate is kind of at once reflecting both that it's less, but as it makes more. Because the elements result that the closures, all the stuff that allow for axiomatics to be complete and consistent, and all the wonderful results of the completeness of arithmetic and all these great things. Nothing wrong with it, just not done yet. All right, so yeah, there's much to be. These are the preliminaries getting into the higher order, the quantum field theory. Nash is very ambitious in his quantum field theory because he's working up a continuum mechanics for it. So, looking to Swanson here, we're reading in chapter 3. 3.1, the free particle. Chapter 3. Evaluating the path integral. In this chapter, various forms of the path integral will be evaluated, thereby demonstrating different techniques. Each form considered will be useful to later analyses and will illustrate the utility and validity of various methods of evaluating the path integral. So it seems that here he's going to begin to describe the contrivances and then how that's carefully applied to the scaffolding, thus not to bring the scaffolding down while raising it. The basic types of approach to evaluating the path integral form are the transition amplitude, the value, what's measured, the observable, can be broken into two groups, discrete methods and continuum methods. And it's about how they add up, or when across the surface, it's like measuring the flow is then as of a product of the surface and the volume and these kinds of things and their ratios. And it's interesting that he breaks it into two groups, discrete methods and continuum methods. In the discrete method, the integral of the action is replaced with a Riemann sum, and the intermediate values are integrated using the measure defined by 2.46 or 2.52. In the continuum approach, the action is treated as a functional, and it is expanded around a set of classical trajectories using Fourier series. So this is a lot similar to what we have going on in Millikan, when he describes that some of the contrivances that allow you to, as he puts it, either to employ the nonlinearities or to lose the nonlinearities is along the lines of this the functionals. That the way you parameterize the values is of a changing value, the input over time. That is to say that what's described is like this is how you adjust the dial as it goes forward, so that there's always just the right amount of pressure to push the string along. It's like pushing a string. And so if it's done at the correct rate and over time, just as it adds up, it has more and more friction over time, you can make that a linear value, a constant value in velocity, but more or less. And then it's no longer, the string does not stay straight. Or for example, then it oscillates on its way out and how it goes. So it's similar to that notion. It's like pushing spaghetti, cooked spaghetti. In the discrete method, the integral of the action is replaced with a Riemann sum, and the intermediate values are by the measure, In the continuum approach, it's treated as a functional and is expanded around a set of classical trajectories using Fourier series. They're like Laplacian, and it's everywhere. The second approach is more difficult to implement exactly, and some aspects of this approach must be inferred from exact results found by other methods. The continuum approach. So the continuum approach helps build up these, basically when it's not in the box, and there are other factors, or it's an arbitrary shape or region, whereas the discrete approach is very controlled. And as to why something that happens in the particle accelerator, and eureka, it's all standard, is often not that big a deal. It's just like, well, it's all standard, and we dialed up the energy, and it's still standard. Depending on how the experiment was defined and derived and designed and put together, it kind of depends who's reading that off, whether they know from that configuration whether it makes a difference or not. If people are unaware of these higher order contributions of the things, then it's possible to contrive the experiment so that they will perfectly validate their own expectations, even though there are others that they simply don't know and don't know when in the experiment. It's kind of like the cool thing you find at the Science Museum, and you, near the end of the Science Museum, it's like exit through the gift shop. Hey, wait a second. Walk past this spiral, this funnel, and it's designed that when you put a quarter in it around the rim, it'll start spinning on its edge, and it'll spin on its edge all the way around in more closer and closer concentric circles as it finally drops into the funnel and funnels down in a spiral motion and does it. But if it's something with a different weight of this object, it will just slide right in. Its orbit is not so contrived according to the rolling versus the sliding of this coin to make it so. It's contrived. It's contrived. So one might imagine that experiments in the high energy are very carefully defined to do two things. One, confirm the standard. Two, provide people in the know who know its fundamental configuration of experiment, configuration of energy, what else they need. And those are people we call physicists and experimental and fundamental physicists. And the other people are called technicians and watch polishers. In section 3.1, the free particle propagator is calculated from the corresponding form and shown to be the exact result found by the operator approach. Section 3.2, the free particle is given a time-dependent driving force referred to as a source. Time-dependent was this idea of that's a functional, or it's differential driven too. And the corresponding form is analyzed. The resulting form can be combined with the functional derivatives to analyze in a very compact way time-ordered products of the Heisenberg picture position operator. This is the linear part, and it's also sometimes and it's the only observable we can get. So it doesn't matter if it would flower into this great other thing. It's the apparatus or the application simply has only that this is what we get. The Heisenberg picture position operator, and S for its momentum operator. This gives rise to the important concept of a generating functional. Generating function is kind of like the generators of series and recurrent relations. The generating is what generates feedback or constructive or destructive resonances that arrive at what it generates. Kind of like how a laser works. It develops a generating frequency. How the Tacoma Narrows Bridge generated a fundamentally terrific harmonic frequency. It is shown that this functional can be used to analyze the motion of a particle in a more complex potential. And here when he says more complex potential, it's kind of as in our complex analysis, meaning it falls off, but if we have other compensatory terms, we might be able to keep it on the track, the wave train, by defining a perturbation series representation of the propagator. This goes directly to these methods from Avogadro. We talked about the non-linear electromechanical effects and applications. There are similar descriptions there as of similar methods for similar purposes of the application methods for totally different domains that happen to admit all being the same kind of models ultimately. In section 3.3, the harmonic oscillator is analyzed using quasi-continuous methods. Quasi-continuous is like pseudo-continuous. Like quasi-invariant measure theory. It's invariant theory, but then there's these exceptions. Pseudo-differential operator. It's differential operators, but with these caveats. The degenerate is what results from some ultimately what leads to an impasse of the induction, but it's not zero, or non-empty, say. Oftentimes that the only opinion of the topology is that that's not so. There are others. Using quasi-continuous methods, then a careful analysis of the Jacobian associated with the change of variables is made. So when he says careful, That means both tentative and general, and also not without its risks or questions, or whether or not it remains well defined. It's well behaved. Associated with the change of variables is made, and that's where it's the change of the variable, whether that reflects also not just the change of the variable as a parameter, the change of the variable as a parameterization. It's like, well, to pump enough energy into it and ended up making it a wave. These kinds of things. In section 3.4, the path integral for a particle on a ring, derived in section 2.4, is analyzed using Poisson resummation techniques to reveal its underlying topological structure, to reveal an underlying topological structure that it has. There are others. Just like there are replete definitions of continuity here, line continuity, field continuity, and signal continuity, there are more replete than sole definitions of topologies, what a topology is, about neighborhoods of particles and critical points and their densities and such, about what's continuous or discrete. 3.1, the free particle. In this section, the simplest possible system, that of a free point mass moving one-dimensionally, is analyzed using the path integral. The Lagrangian is given by Lagrangian of q dot q equals 1/2 m q dot squared. The system can be analyzed very easily by operator techniques, since the associated Hamiltonian is given by hpq equals p squared over 2m. So script EL, here's the Lagrangian, sometimes it's the Laplacian. Laplace and Lagrange are about in that order, are from the French school, before Cauchy, I guess you'd say. But after the Bernoullis and such, that was where the strength was. Using completeness of the ket eigenstates in the form of the inner product, a transition element can be written. Z of QBTB QATA equals bra QB given e to the I h TB minus TA over Planck h bar given QA, Hamiltonian in the middle there, equals the integral from negative infinity and dp of the exponent dot equals of the negative I times quantity p squared over 2m Planck h bar TB minus TA of bracket QB given P and bracket P given QA. That anti-commutative adding back up there. The commutative relations that make for the symmetries that add up to walking the line. These line elements, the transition elements, which are in this Jordan measure, this 1.0 of its path. Each one of these paths in the space of these paths that the author has described, each one discrete and emitting all that the other ones exist and are there, but are just they're beneath the floor, as it were, so that they provide a finite value that happens to meet up with these other reasonings that altogether it stays the course. This is a Gaussian integral of the form so that the final result is z of QATA QBTB equals m over the quantity 2 pi I Planck h bar TB minus TA quantity, square root of that, times the exponent of I over Planck h bar m QB minus QA squared over 2 TB minus TA squared. So in this sense, that it's a Gaussian integral is really that's where I feel like my ignorance lies. And so I'm wondering about how to better understand the Gaussian integral and the complex analysis and the branches of complex analysis and the considerations of how Gauss uses the synthesis of the arithmetic in the complex field, and about how that it has identities that fall back into the real values, and that otherwise that it has that certain particular quantities accumulate in the ring, and that the complete ordered field and the real fields are both a ring of numbers, that they have addition and multiplication in the distributive law, and besides the associativity and commutativity of their elements and the existence of identities and inverses. This is then that what I'll be trying to figure out, that because the space has so that there's kind of like the principal inverses and stuff, because it already starts with that I is the principal square root of -1, but negative I is also a square root of -1. Even from that gets into all these things that go into the descriptions, the definitions, the derivations, which results like complex analysis really needs to be laid out as like, this is the field of complex numbers. Instead of spending the whole course showing you each of these different little developments that arise once we get through each of these proofs and theorems and exploring a bit around, here's all the definitions up front about the only operations we're going to apply in this field of complex numbers. And here's all the interpretations we're going to make. And this works out all the rules about them, and we're going to have an algebra of Gauss's complex numbers. And so that way we can separate that in a model of that from what would otherwise, for example, be an extended algebra of more than Gauss's complex numbers. These are the kinds of things that get left behind. And especially as it gets more and more built over time that this is the classical way and all this has to be like so, it becomes very intractable to dig them up. This is the old dilemma. It's like you have built a fence a mile. All you have to do is move it a half foot to the side. This is it's quite intractable. And so it's a similar kind of idea about how to go with these descriptions and reasoned and seasoned and deliberate descriptions of the derivations after definitions to help it so follow that it's possible to build back lower level thinking. That the degenerate and the pseudo-quasi result a whole again. And so that gets into a lot of these things, even this idea of deconstructive criticism. As a literary entail, is for our physicists then to figure out how we can help mathematics again, provide this repleteness in its theories of its superclassical that it needs to arrive at then this reconstructive. Makes for, just like when we talk about that discretization of the quantization is a denormalization, but with regards to the real wave function, that it's renormalized. That this renormalizing and these renormalizing operators are how it's arrived at, that after all this quantum path integrals, for the discrete case, it still results in a straight line. And that it does. In terms of these other contrivances and conditions, as where and how it doesn't. So that'll be nice. And so that's kind of some reading. It's getting started in chapter 3 of Swanson's book on path integrals and quantum processes. See, I picked up some books here. What is this? This first book is a book by Irving Chernoff. It's called Logical Chess, Move by Move. And it's a pretty great little book. And what it's got in it is that he addresses each chess game and each move not only with the thrill of a spectator, but also with a comment on each one, what his thinking is about the development of the offense and defense and the situation and the contingencies and the plays and the line. And so I think chess is quite difficult, and I never really developed an intuition about it, though I know the rules, and the rules are few, and once they're well understood, then anybody can play, and it's a fair enough game because everyone has the same rules, and it always starts the same. So there's something to be said for that. Not that everybody has the same means, although I believe certainly for fair games that you need to have it that the handicapped is not the handicapper, and that you get some extra strokes for being poor, not that someone who's good gets any more strokes. And so that's the kind of thing when it goes into games and gaming and the theory of games and the theory of winning and losing games and all that kind of stuff. And then there are zero-sum games and what with regards to games that are competitive, and games that are collusive. And as to why collusion isn't necessarily a bad thing, but it usually means colluding at the cost of somebody else. Competition or cooperation, I suppose, is the positive framing of that, whereas conflict or contradiction are these other complementary reflective terms who reflect the same things in terms of each other, kind of left and right and left, then whether even these sets of terms are to each other right and left and right. When the right-hand rule is just thumbs up, so that's the kind of usual thing. Then these other books is so if this is kind of a treatise of a course of a means of chess appreciation for turn-based strategy games. Then these other books is what's called comprehensive chess openings. And so this is by Y. Estron and V. N. Panov, or something like that, from Pergamon Press. And so this 3-volume edition from Pergamon Press is called Comprehensive Chess Openings. So when we talk about games like chess, it's basically divided into 3 things. And one is called the openings, and that's how the game starts. And the game is afoot. The game is there's an onset of the game, the outlay of the game, the outset of the game. So the openings lead to the initial conditions that establish these kernels, these seeds, these initial values. Then there's the game. The big game begins. The game proceeds, and then there's the mid game, which is everything that goes on in the course of the shifting concerns and the interplay and trades and this sort of beginnings and endings, while there are 2 conditions that it's not the end game. The first condition that it's not the end game is that an inexorable advantage one way or the other is established and exploited. That's an end game. It results in the game of chess that the chess ends when a player is in checkmate, meaning that their king is threatened and there's no way they can take that piece or all the pieces that threaten it, and nowhere it can move that it's not threatened. Right? And that the game of chess there's a board of 8 by 8 squares, and there are 2 players, and they take turns, and you may not skip a turn. And on each turn, the player moves one of their pieces, and each of the pieces has particular ways it can move, some back and forth on the board, and pawns only forward, or rather across, or diagonally in attacking. Pawns only attack and capture the opponent's piece diagonally. And then there's only one move that exchanges the pieces exchanges the positions of 2 pieces, called the rook and castling, rooking, and that's where the king and rook, if they haven't moved yet in the game, can on the one side change places, and on the other hand almost change places. That the rook arrives at a spot next to the king, and the king arrives over on the other side of the rook. So that said, then otherwise the one asymmetry of the game is that according to the way it's played, that white goes first, and the way the board is arranged is that the king and queen are asymmetrical pieces that otherwise is symmetrical to the left and right of the center of the board in the way the board is set. And then the king and queen are different pieces. The queen can move in any direction in a straight line, any number of spaces, and the king can only move one direction in any direction, one many places, or as according to the castling as before. And that the knight is the only piece that can jump over other pieces, as in the intervening pieces do not block it. That a piece may not move through other pieces that block it, and besides the pawn and its capture, any other piece can move, and if there arrives at the last spot where it moves is an opponent's piece, that it captures that piece, replaces it, and removes the captured piece from the board. Captured pieces never are put back on the board. Some have a rule, and it's pretty usual, that if a pawn reaches all the way to the far row of the opponent, that it becomes a queen. And some even that it isn't necessarily that the queen has left the board for another queen to get on the board. And that usually is pretty close to an end game situation right there. So the mid game is the bulk of the game. And then the end game is either a short or the long end game, because the short end game is kind of when there's an intractable situation and it's gone awry either way for one of the players, and that the other one wins thereafter briefly. And then there's the long end game of sorts that results that if the game is short or long, it kind of results that whether the mid game is short or long, what results is the end game is when it's kind of resolved that they're either playing out an end game or the jeu is fini, the game is up, or what, as they say. So I've been learning a little bit from this logical chess move by move that there's a guy named Steinitz who says a lot of things. Vacating a square for the king, black abandons the projected 15 pawn to bishop 4. Against this, Tarrasch intended, according to his own comments, and he lists a bunch of moves here, pretty zigzagging by the queen, and quick mate follows. To keep black shook out, and then 20, boom, with an easy win. The winning move, although it appears that white has been playing a long string of winning moves. Pressure is now redoubled on the rook pawn, with white threatens to win by either by 17 bishop, king, knight, followed by 18. The language of chess games, and you can find all the symbols of a chessboard in Unicode and other similar to that. You can find musical notes and their kind of things. That musical notes and chessboards represent a lot of different things to do with strategies and moves and games and combinations according to these pieces. And something like computing what the knight's tour can be is our usual exercises in paths and graph theory and this kind of thing. So anyways, then so this is basically some game appreciation stuff, and the strategy and the tactics, where tactics are short-term atoms or elementary operations that result in overall strategies, that the strategies of a strategy make it so that the what's important is the strategic, but it's implemented in terms of the tactical and this kind of thing. And then this comprehensive chess openings is basically an enumeration, a common enumeration of sorts of all the different ways a chess game could start. A gambit is an opening which is a risk, taking a risk hoping to exploit an opponent's ignorance or unawareness. The chances are level. Greco-Philidor gambit. This is many gambits. King's gambit declined. And it goes on that all these kinds of chess games are very cataloged, and there's a whole culture of them. This opening, the Vienna game, worked out by Viennese masters during the middle of the last century, was intended to prepare the gambit move pawn to king's bishop 4 without allowing black to carry out the counterblow. Pawn to queen 4 is in the Falkbeer counter gambit. However, black can quickly achieve good counterplay, and the opening is rarely adopted nowadays. Some people have a catalogic memory of how to advise them to go quickly to considerations of what is already established would be the closure of conditions that make for good strategies. So these are pretty great books, and it's hard to find a replacement for them in the sense that something like this Comprehensive Chess Openings is the Comprehensive Chess Openings. But then when you get in terms of, even insofar as how it breaks things down, gambits, open games, semi-open games, and closed games, that here it's establishing, just as we've been talking about the degenerate and the open and the pseudo and the quasi and the closed, that here it's as well establishing that there's a very natural correspondence between that and these kinds of these interactions. And it's kind of where, when you think of the least action potential and these models of things, if you consider a flow of volumetric fluid across a grating that's square, then you can think of it in terms of that flow is uniform over the whole thing, and that it just has to result that in terms of from the beginning of the pipe, stuff's going in, the end of pipe, stuff's coming out across any given section of that pipe, there is this grading. And so if you take that grading and have it be a square lattice, then you can say that, well, just as so that it's all got to be uniform across that, you can also think of it in terms that it's all the eddies and the back and forth across that just add up to that 1.0 forward flow. But what happens when there are eddies in the current? And so something is actually, it's in some point various in terms of that pulsation and that pressure as it comes across, that flow, and even including how it could be negative or what. And so there's an idea of you can divide that in terms of Latin squares and say, well, we'll just break it down in terms of each of the rows or each of the columns has the same sum and they're uniform. So like that laminar flow is established. And then still, then you can just say, and then we'll just make it random what all those other things are to make this model of what happens when there's turbidity or vorticity. And now it's similar when you can make it, well, just make it a magic square instead of each of the rows and columns adds up, that you can make it so like so. So Latin squares and magic squares. So I relate that to this comprehensive chess openings and the open, semi-open, and closed games, because it's similar when you think about the action potential across, say, a capacitor. Capacitor has a gap. You just got a voltage differential across the gap. Until there's an arc, there's no current. When the capacitor closes, when it reaches breakdown voltage, or what you might call the capacitance voltage, excuse me, I'd have to correct my terms, then it jumps. And then as to which way it jumps and as where from, you can think of it in terms of a potential flow, because it might jump either way to get started. Arc. And so this is the kind of thing then when we define that, besides you have to determine games in front of all these different things and strategies and coordinations and roles, then it's so similar when you think of it in a game theory in just terms of that, in this superposition like quantum theory, they're playing all the games. And so that's just a way to think of quantum theory as the same thing as game theory. And as from a superposition of all the games, it works out that there's a path and course through the game and then milieu in the middle. And that's also our observables and kind of what we see. And so then when we get into the descriptive, is like why people make moves, and then these thorough and these organized and the comprehensive about what all they went through. And it's quite a thing. And these days, yeah, I suppose I enjoy chess. I have 3 or 4 chess boards and a little magnetic travel kit. I don't play it though. I find as much as I find people who enjoy playing, they thrash me quite soundly. It's like I was talking to a fellow the other day. I was like, well, how did you like growing up? He's like, my dad was a chess master and I am pretty good by now. And this kind of thing, you know. Then there's something though like Civilization 6 or Sid Meier's Civilization 6. So Civilization is kind of like an open-ended chess game, but instead of an 8x8 board, it's got about a 500 by 500 board. And these days it's hexagons instead of squares in terms of the tilings of the board. So the board is basically a globe, and so it's treated as a globe, and it's kind of like dragon chess, which is this idea, which is you have 3 different boards and you can go above and below, and so pieces can also move in these arbitrary ways and this kind of thing. And so then the key things of that are similar with the openings in a mid game and an end game. And so for something like random side, emperor difficulty or handicap, standard rules, standard time, and small continents, and a huge map with 12 different players, then I win a good percentage of the time. I win more than half the time at this level. So I've been playing it a lot, and I have a lot built into my tactics and strategies and da-da-da. And the key is basically to get pieces on the board, because you have to get pieces on the board early, because that's the only way to possibly get enough of the bonuses, accelerators, and the upgrades that make it so that in a fair game, it involves learning the rules too. There's a much more expanded rule set. And though that it ends up becoming pretty much standardized and all that kind of stuff. So for something similar to like the real-time strategy game StarCraft, which was the competitive milieu of real-time strategy games for a long time, and turn-based strategy games like Sid Meier's Civilization, or for something like Red Alert or Command and Conquer Red Alert, or what else? There are all these kind of real-time strategy games, real-time tactics games. Indeed, I tend to find those more so on the computer. Though at one point in time, I was in the top 100 in the world in Red Alert 3. Not for very long, but online. So anyways, then when thinking about these things and then figuring out the systems of games and what's the stochastic behavior of these things over games, it's not so much different than the stochastic behavior of the particle, but here it says above, instead of a rational agency solely focused on this one game, it's all of science just gently flowing in its principle of least action. So it's a real wave function, and that's how it's to be right with things, this superclassical kind of notion. And you can too. Well, all right then. Hey, have a great day, and I hope it finds you as well or better tomorrow. So long.